Welcome to Calculus. Being challenged has a whole new meaning. On this episode, Stevenson will demonstrate we have studied so many derivatives at this point. So you may be wondering, how can we have so many more derivatives? Well, it all depends on the family of functions. We have trig derivatives, right? Those 6. We have functions that are raised to some power, some rational power. That's power rule. And now we have exponential and log functions. So let's look at our first rule. This first rule tells us that if we want the derivative of an exponential function, a represents the base and u represents the exponent. If we want the derivative of an exponential function, all we do is we write the exponential function itself again. We multiply it by the natural log of the base only, and then we have the product of the du dx. What this means is then take the derivative of the power. This applies chain rule. So what we're saying here is, what if our exponential base has a power of another function? So essentially the derivative is the function itself times the natural log of its base times the derivative of its power. So let's demonstrate an example here. Look at example 1. This is question 14 from the textbook. Y equals 3 to the power of cotangent of x. So in this particular case, 3 would be my base, which is a, and cotangent of x is my u, or in other words, my power. So according to my rule, my derivative in this case would just be the exponential function itself, the natural log of its base. Well, in this case, the natural log is, the base is 3, so it's natural log of 3 times now du dx. Well, that's the derivative of cotangent. The derivative of cotangent is negative cosecant squared. So you could stop here, but remember, natural log is 3 is a number, it's a constant, so we could do a rewrite. And that is your derivative. As messy as that seems, that's it. You could also put some parentheses like this just to make sure that you don't get confused and assume that any of these quantities are actually inside the cosecant function. Let's look at another example. Example 2. Now in this particular case, you may be wondering, but Stevenson, there's no exponential function here. But let's look at this structure. This is a cosine function on the outside, but inside it has that exponential function. So we're going to use chain rule here, but in the process, we're going to do derivative of the outside function with the inside left alone times the derivative of the inside function. When we do the derivative of this inside function, because it's exponential, we have to use our new rule. So let's begin. The derivative, the outermost function is cosine. So its derivative, remember, sine, cosine, plus, minus, minus. The derivative of the outside, because it's positive cosine, we can see it's going to be negative sine, times now the derivative of the inside function. Well, again, it's exponential, so we're going to follow our rule. So the derivative of 5 to the power of x is itself 5 to the power of x times the natural log of 5 times the derivative of its power. That's the u. See, that's the du dx. Well, the exponent is just an x. What's the derivative of x? 1. So you can do a little cleanup here. So this is an example of your exponential derivative. Now there's a special case. What if your base is e? Okay, now we're still going to use the same exact rule. However, something different is going to happen. So in our process at the end, we're going to end up with our other exponential rule. So I'm going to find the derivative. Now remember, I'm still going to follow the exponential rule, which tells me to do, so the derivative of an exponential is the exponential itself times the natural log of its base times the derivative of the exponent. Well, the exponent is 3x, so the derivative is 3. Now I want to point out something to you. This should stand up to you. You should look at that and go, wait, I know what that is. That is 1. Why? Let's do a very quick review on natural log here. Remember, logs are exponents, right? And remember, logs and exponents, let me rephrase that. Logs and exponents are inverses of each other. So remember, natural log means the base is e. So if I'm evaluating natural log at e, I'm basically saying the natural log of e base e equals what? So if I convert this to exponential form, it says e to what power is e? Well, what would the question mark have to be to make this true? Hopefully you see it has to be 1. So what this means, therefore, the natural log of e is 1. So essentially, to sum it up, if you take the log of a function inside or of a value of side that matches the base of your log, it's always going to be 1. Now, why is this important? Well, look what happens. End up with 3e to the 3x. What this means is that because we took the natural log of e, this natural log of the number, like we saw in our previous examples, just becomes 1 every time. Now, do you see a shortcut to go from here, the problem, here to the answer? Let's try one more, and let's see if you can figure it out. Prime equals, so this is an exponential, so we're going to go e to the power of x squared, because remember the derivative of the exponential is the exponential itself times the natural log of its base, which in this case is e, times the derivative of the exponent. Well, that's x squared, let's use power rule. The derivative of x squared is 2x. Natural log of e is 1. Did you figure out the rule? Did you see it in your notes? If not, here's the rule. What it says is if you do the derivative of an exponential where the base is e, then it equals the exponential itself times du dx. Why is there no natural log? Because when you take the natural log of the base e, what will you always get out? 1. So essentially, the derivative of e to the u is always itself, e to the u. And then you just multiply it by whatever the chain rule is of the derivative of the power. So the derivative of e to the u is one of the easiest derivatives you will ever do outside of power rule.